In this section, we're going to talk about simplifying radicals as well as fractional exponents. First, we need to talk about the key parts of a radical. Now, that radical sign that you see there, a lot of us have known as the square root sign. And that's because of a very important piece of information that is called the index. So in this diagram, the index is notated as an n. Now, if there is no index, then we assume that the index is 2. Okay, and the 2 is what signifies us to take a square root of something. Some more vocab. This is what we call a radical sign, and this is what we call a radicand. Okay, the underneath part of a radical sign is called a radicand. So when we are talking about simplifying radicals, we do want to remember our perfect squares. Some of our perfect squares are numbers such as 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and another perfect square that we don't really think about a lot of the time is in fact the number 1. Okay, the square root of 1 is always going to be 1. It's a number that a lot of us forget about when we're talking about simplifying radicals or perfect squares. So if we look at the first 4 examples, perfect square roots. So 16, we know that 16 is in fact a perfect square. Now we have to think about what the square root of 16 is. We have to think backwards. What times itself is going to give us 16? And that answer is going to be 4. Now it gets a little more complicated when we have something such as number 2. This 2 on the outside right here is being multiplied. So we're going to have 2 times whatever the square root of 121 is. The square root of 121 is equal to 11, so this is going to reduce to 22. And you guys can do the next 2 examples if you wish. Now, the hard part becomes when we don't have a perfect square that we're simplifying in our radical. There's 2 ways in which we can simplify a radical. The first is going to be the way that these 3 steps break it down for us. The first one is finding the largest perfect square that the radicand is divisible by, and then breaking down the radical using that number. So let's try number 5 doing it this way. So if I'm thinking about 32 and thinking of my perfect squares, what is the largest perfect square that 32 is divisible by? Hopefully you all said 16. So really this can transform into square root of 16 times 2, right? Isn't that what 32 is equal to? And then we can break this into the square root of 16 times the square root of 2. We know that the square root of 16 is equal to 4, and then we write what's left over underneath the radical sign and keep it there. So our final answer should be 4 root 2. Now, if thinking about those multiples or what the largest perfect square is that you can divide a number by is a little challenging, then we can use factor trees. We can use a factor tree in order to simplify that radical as well. So by using a factor tree, we would take 32 and we would break 32 down into its prime factorizations. So that would be 2 and 16, 2 and 8, 2 and 4, and 2 and 2. We want to break it down into its prime numbers. So 2, 3, 5, 7, 11, 13, any of those numbers. So now what do we do with the factor tree? We now look to the index. And in this case, there's no index written here, So we know that our index is actually a 2. That index is telling us how many of a kind I'm looking for. So I'm looking for 2 of a kind. I have 2 of a kind of 2's, another 2 of a kind of 2's, but then I have this 1, 2 that has no perfect match. So what happens is these 2 perfect matches will come out of their radical as a single. So we end up with 2 times 2 on the outside with what's left over on the inside that doesn't have a friend. So this is going to reduce to 4 root 2, which is the exact same thing that we got when we used the first method. So either one of those methods is completely fine. It just is whatever you feel more comfortable with. Let's take a look at number 10. I'm going to do number 10 using factor trees. So I have this 2 that's being multiplied outside my radical. That's going to be really important in the end of our problem. So let's first break down 54. 54 is 2 and 27. 27 is 3 and 9. 9 is 3 and 3. Once again, I have no index, so my index is a 2. I'm looking for pairs. So I have 1 pair of 3's, and that's it. So this 2 that's being multiplied on the outside still needs to be multiplied on the outside. This pair of 3's, that gets multiplied on the outside. I write my radical sign. What's left over is this 2 and this 3. Those get multiplied on the inside. So I simplify all my multiplications for a final answer of 6 root 6. Now, one very important piece of information. If I have the square root of, so this is a big key piece of information, very important. If I have the square root of -5, okay, first of all, 5 is a prime number. Also, this negative under the radical sign, that negative under the radical sign is not allowed for our purposes. This is automatically going to become no real solution. Yes, the word real is important. If your answer does not have the word real in it, that is incorrect. There is a solution, but it is called an imaginary solution. And we're not going to touch on imaginary solutions. So for our purposes, there's no real solution, and that is our final answer. And that's only when a negative is underneath the radical sign. We're going to look at multiplication and division rules, and then we're going to go back to cubes. So, multiplication of radicals. So if I look at number 2 right here, multiplying the radicands using what we call a product rule. So if I have the square root of a times the square root of b, I can really multiply those underneath my radical as well, as long as my roots are the same. So, for instance, number 1, I have 8 times -3 times the square root of 2. So that -3 is going to come out in front. I have a -3 on the outside. What's underneath my radical, I can multiply together. So now I have -3 times the square root of 16. Square root of 16 is just equal to 4. So our answer should be -3 times 4, which is -12 as our final answer. So anytime you have them split apart, you can always multiply them back together underneath the radical sign. We're going to skip down to division rules. Once again, the quotient rule, you can also break apart your quotient. So this, what I mean by that is we would have the square root of a over the square root of b. Sometimes it's easier to simplify the square roots as one fraction. Sometimes it's easier to break them apart. So for instance, if I'm looking at number 1, that fraction as a whole doesn't reduce. However, looking at that fraction, they have a perfect square on top and bottom, so I'm going to break them apart. Square root of 49 over the square root of 100. This is going to reduce to 7 over 10 as my final answer. Whereas if we skip down to number 7, square root of 3 is not a perfect square. Okay, 96 is not a perfect square. However, if I change this to one fraction, 96 over 3, if I reduce that fraction, 96 divided by 3 gives me the square root of 32. 32, I can reduce this radical. So let's make a factor tree. We're going to have 2 times 16. 16 is 4 times 4, 2 times 2, and 2 times 2. I look for my 2 of a kinds. I have 1 2 of a kind, 2 2 of a kinds. That comes out as 2 times 2. What's left over is this 2 on the inside. So my final answer here should be 4 root 2. So let's go back to the cubes real quick. Cube roots, okay? Perfect cubes. The most commonly used perfect cubes are going to be 1, 8, 27, 125. So the cube root of 1 is 1, as always. The cube root of 8 is going to be 2. You have to think about how many times something times itself will give you that number. So 2 times 2 times 2 is 8. The cube root of 27 is equal to 3. And the cube root of 125 is equal to 5. So let's go ahead and take a look at number 19. So I have a non-perfect cube root. I already know that it's giving that to me in my instructions. So I'm going to break down 40. 40 we know is 4 times 10, 2 times 2, and then 2 times 5. Now remember back when we were simplifying square roots, our index was a 2, and that was telling us how many of a kind we needed to find in our factor tree. My index is a 3. That's how many of a kind I'm looking in my factor tree. So I have 3 of a kind of 2's. It's going to come out on the outside as 2. We have to remember to write our index and our final answer. What's left over is 5, and that stays inside. So our final answer should be 2 times the cube root of 5. Let's do one more with a multiplication on the outside. So 21. Now we're looking for the cube root of 423, or 432, sorry. 432 is going to be 2 and 216. I think it's just easy to start with 2 and keep dividing by 2 until you can't go any further. Now 27 is 3 and 9 is 3 and 3. Now that's a lot. And we have to remember not to forget about this 2 that's being multiplied. So I'm just going to bring it over already. So we have 2 times something, and then we're going to have the cube root of whatever our remainder is. So let's look for our 3 of a kinds. I have 1 3 of a kind of 3's, 1 of 2's, and then I have a 2 left over. So we're going to multiply the 2 and the 3 on the outside, leave the 2 inside. It's going to leave me with 12 times the cube root of 2 as my final answer. So the only thing that changes between simplifying a square root and simplifying a cube root is how many of a kind you're looking for, and that's always going to change based on your index. Now our last topic, rational exponents. Now you would think that why are we combining a rational exponent, so a fraction in our exponent, with radicals? Well, a fraction in our exponent actually represents the root or the index or a radical. So basically what's going to happen is if I had something like 145 to the 2/3 power, the 145 is my base of this exponent problem. It then becomes my radicand. Next, my denominator becomes my index. And lastly, my numerator is now the power on the outside of my radical sign. So if I look at this first example, 27 to the 2/3 power. Anytime I see a fraction in my exponent, my first thought has to be to turn it into a radical. So I'm going to rewrite as a radical with 27 as my radicand. My denominator is the 3, and that becomes my index. My numerator is a 2, and that becomes my exponent on the outside. We break down our 27 into a factor tree. We end up with one set of 3 of a kind that goes inside our parentheses as 3. 3 squared gives me 9 as my final answer. So let's go ahead and take a look at number 2, 81 to the 3/2 power. I see a fraction in my exponent. I know I automatically need a radical sign. 81 is my base, so it goes underneath. I have some parentheses. My index is my denominator, so that becomes a 2. My numerator is my power, so that goes up top. So rewriting this without all those little lines and things, we're going to have the square root of 81 to the 3rd power. 81 is 9 times 9. I can even just stop there, right? 81 is a perfect square, and it's going to be 9. Now we have to bring down our parentheses. 9 to the 3rd power is going to give me an answer of 729. Let's go ahead and look at number 4. I have a 216 to the 1/3 power that automatically becomes a radical with 3 as my index, 216 as my radicand, and my exponent is a 1. Let's break down 216. 216 divided by 2 is going to give me 2 and 108, and 2 and 54, and 2 and 27, 3 and 9, 3 and 3. My index is a 3. I'm looking for 3 of a kinds. I have 1, 2, 3 2s, 1, 2, 3 3s. My parentheses stay, and on the inside I have 2 times 3 with an exponent of 1. So my final answer here is going to be 6. And that is simplifying radicals as well as fractional exponents.